Hi, my name is Adam Anderson. I want to tell you about a new camera that we're developing called SPT-SLIM for the 10-meter South Pole Telescope, shown here. The goal of this project is to demonstrate a new millimeter wavelength spectrometer technology called the on-chip spectrometer, and use that technology to do a line intensity mapping survey. So what is line intensity mapping? Well, it's an emerging observational technique that involves measuring the total emission of a redshifted atomic or molecular line, for example, from carbon monoxide or a singly ionized carbon transition, which you can measure at high redshift in the millimeter. You can use, if you have a spectrometer, you can use that frequency resolution to resolve the emission from each redshift slice and construct a three-dimensional map of the emitting matter at high redshift in the universe. The emitting matter is itself a tracer of the large-scale distribution of matter in the universe, and so therefore you can learn and infer what that distribution looks like, and thereby learn about cosmic history, learn something about cosmological parameters. And this turns out to be better at probing the high redshift structure of the universe than galaxy surveys, which have to threshold on individual galaxies. So in individual galaxies, the ladder of rotational transitions of carbon monoxide molecule, as well as the transitions of C2, singly ionized carbon, are among the brightest lines from individual galaxies. And yet, the power spectrum of the aggregate emission of CO and C2 at high redshift have still not yet been conclusively detected. So this presents something of a discovery opportunity. You can see down here models of what the power spectrum of CO should look like, which have quite a bit of uncertainty. And here in yellow and pink, you can see just a few upper limits and weak detections of the CO power spectrum. But future high precision measurements of CO and C2 at high redshift could be potentially a very useful tool for constraining cosmological parameters and learning about physics like inflation and the history of the very early universe, neutrino masses, whether there are new light relic particles beyond the standard model, as well as the nature of dark energy. So what we're interested in doing with SPT-SLIM is exploiting the 10-meter South Pole Telescope as an observing platform to demonstrate these new spectrometer technologies for doing a limb survey. So SPT is this proven 10-meter CMB telescope that's observed for many years at 90, 150, and 220 gigahertz. And crucially, it can observe both in the austral winter, when the conditions are comparatively very good, as well as in the summer, where data is still usable, even though it's not good as the winter. So our strategy is to mount a small receiver containing these new detectors in a location in the optics chain of the South Pole Telescope that allows us to put an extra mirror, pick off some of the light, and observe at the same time as the main receiver, SPT-3G, is installed on the telescope. And the idea is to install this receiver, this new SPT-SLIM receiver, for the next 3 summer seasons starting this year. What do these spectrometers look like? How do they work? Well, the small signal that we're looking for, as well as the need for having frequency measurements, redshift resolution, requires having a high-density, mass-producible spectrometer technology. And this technology, new technology called the on-chip spectrometer, really fits the bill. It combines both the filtering technology, the spectrometer, as well as the pixel on a single mass-producible silicon lithographed wafer. Light comes in, is picked up by these probes, and the pixel is sent to something called a filter bank via microstrip, which basically consists of a set of narrowband filters, each of which is coupled to a kinetic inductance detector, a kind of highly multiplexable detector. The frequencies of each of these filters are offset slightly, and so they can be combined into a band that spans a relatively wide bandwidth, in this case from about 120 gigahertz to about 180 gigahertz. And the full focal plane of SPT-SLIM will consist of 12 of these pixels, each of whose polarization modes are coupled to 2 filter banks with a resolution lambda over delta lambda of about 200. So we've been hard at work at developing the hardware that will be needed to deploy for SPT-SLIM. At Fermilab, we've been designing and are now building this ADR-based cryostat. It uses a very compact design and will contain a focal plane consisting of these 12 pixels divided into 3 submodules, which has been designed by our collaborators at Cardiff. Prototypes of these filter banks have been fabricated and measured by collaborators at Argonne National Lab. This is showing the large number, hundreds of resonant frequencies, each of which corresponds to one of these kinetic inductance detectors, which are measured and characterized with electronics that have been built by our collaborators at McGill. All this is being prepared for deployment later this year, where we'll be happy to see how it works on the sky. Thanks.